imagine you're blindfolded
Right.
and you are dropped into this completely unfamiliar, just massive multi-story house.
Oh, that sounds like a total nightmare right off the bat.
Right, it's terrifying. And then somewhere in the distance, a telephone just starts ringing. Your task is to find that phone.
With a blindfold on.
Exactly. You
So-
can't see the whole house. You only know what's immediately in front of you. So maybe, your hand brushes a wall, or you feel the open space of a doorway,
Uh-huh.
and you have to rely entirely on how that distant ringing is just sort of echoing down the hallways to guide you.
Yeah, you're just feeling your way through the dark, basically.
Right. And that terrifying feeling of navigating the unknown using just like limited local geometry, long-range sound. That is exactly what we force artificial intelligence to do in these virtual environments.
It really is. I mean, it is a monumental challenge of perception and navigation.
But the crazy thing is, for the last 5 years, these AI agents have essentially been, stumbling around in the dark with a terrible memory.
Yeah, they really have. For an AI to actually succeed at this, it has to excel at what the industry calls audiovisual navigation, or AVN.
AVN, right?
Basically, an agent is dropped into an unmapped 3D environment and tasked with finding a specific sound source. And to pull this off, it receives just two streams of data.
Just two.
Just two. First, local visual geometry. So specifically, these are depth maps showing the immediate obstacles right in front of it.
Like the digital equivalent of putting your hands out in front of you.
Exactly, yeah. And second, it gets long-range auditory guidance in the form of binaural spectrograms.
Okay, so depth maps for sight and spectrograms for hearing. But the core problem here in this deep dive, it isn't simply, moving the robot's legs or wings.
Oh, no, not at all.
It's how the AI actually processes those two senses and remembers them as it moves through the space. So today we are unpacking a state-of-the-art framework called Samba,
Yes.
which was introduced in this foundational paper called A Hybrid Mamba for Audiovisual Navigation. And this framework, it finally takes the blindfold off.
It really does. It's a huge leap.
But I feel like before we get to the solution, we kind of have to look at why the old standard is fundamentally broken.
Yeah, we definitely do. Because the field of audiovisual navigation has seen, honestly, a pretty significant stagnation since about 2020.
5 whole years in AI time is like a century?
It really is. And developers have just stubbornly relied on two main tools this whole time. For processing the sensory inputs, so the audio and visual data, they lean heavily on convolutional neural networks.
CNNs.
Right, CNNs.
Yeah.
And then for the memory side, tracking the state of the agent over time, they use gated recurrent units, or GRUs.
Okay, wait, I actually have to push back on that first part.
Sure.
Because, CNNs are like the absolute workhorse of the AI vision world.
Yeah.
Right? They're the gold standard for image processing.
They are, absolutely.
And a spectrogram, if I'm understanding it right, is really just a visual representation of audio. It's like a picture of a sound. So why in the world would a CNN fail when it's looking at a spectrogram?
Well, the failure actually comes down to what the axes of a spectrogram represent.
Okay.
When a CNN looks at a photograph of a cat, let's say, it uses a local bias. It scans small, localized patches of pixels to find, an edge, a texture, maybe a whisker.
Right, it's looking for shapes in space.
Exactly. In a photograph, spatial relationships matter. But on a spectrogram, the axes aren't space, they are time and frequency.
Oh, I see where this is going.
Yeah.
If the CNN applies that same sliding window, that small patch over a spectrogram, it's not just looking at a patch of physical space.
No, it is literally chopping up time.
Wow.
The authors of the paper actually call this time-frequency fragmentation. When a CNN processes a spectrogram through those local operator transformations, it actively disrupts the global time-frequency topological dependencies.
That is a mouthful. Let me see if this analogy works. Tell me if I'm off base here.
Go for it.
Using a CNN on a spectrogram is almost like looking at a massive, complex painting through like a cardboard paper towel tube.
Oh, that's good.
Like, you might perfectly identify a single tiny brushstroke of blue paint, but you've completely lost the composition of the whole scene.
That paper towel tube analogy captures the limitation perfectly, because the agent might detect a specific frequency cluster in that little window, but it loses the broader relationship of how that sound evolved over, say, a 3-second window.
It totally scrambles the context.
Exactly. The agent gets completely confused trying to figure out if a sound is like a fresh acoustic signal coming from a doorway on the right, or just a delayed echo bouncing off the wall on the left.
That sounds like an absolute nightmare for the perception layer. But the memory layer, the GRUs you mentioned, they have their own massive flaw too, right?
Oh, yeah, they definitely do.
The paper calls it representation dilution. What does that actually mean?
So GRUs suffer from non-selective state updates,
Okay.
which means as the robot moves through the environment, it's taking in new visual and audio data at every single step, right?
Yeah.
And the GRU just indiscriminately mashes all of that historical data together.
So wait, if the robot is walking down like a 50-foot, visually identical, completely silent hallway, it's logging all of that empty, boring space with the exact same weight as the moment it actually heard the phone ring.
Yes. It dilutes the critical acoustic signals, those specific directional cues of the target, with redundant, completely uninformative environmental observations.
That's terrible.
The memory center basically just fills up with junk data, and the agent completely loses track of its goal.
Which means the AI is functionally deaf to any nuance, and it possesses this incredibly cluttered memory.
Exactly. It's a bad combination.
So how does the new Samba framework actually fix this hearing problem, like without chopping time into pieces?
Well, the paper introduces something called the Audio Mamba encoder, or the AME.
Okay, here's where it gets really interesting. How does the AME work?
So the Audio Mamba encoder, it completely abandons those local CNN operator transformations we were just talking about.
Throwing away the paper towel tube.
Exactly, throwing it away. It's built on selective state space models, or SSMs, and it utilizes this mechanism called global selective scanning.
Okay, but how does that actually process the sound differently than the CNN sliding window?
Yeah.
Because the technical mechanism here is fascinating, especially starting with how it tokenizes the audio.
Right, so rather than looking at the spectrogram through that narrow tube, the AME flattens the cross-dimensional features.
Flattening it out.
Yeah, it linearly merges the channel and frequency dimensions and projects them into this hidden space. So this basically constructs a discrete, flattened sequence of tokens that represents the entire spectrogram.
Oh, wow. So it takes the whole painting, cuts it into these long sequential strips, and just feeds it into the model so the AI can read the entire narrative of the sound from left to right.
Yes, that's exactly what it's doing.
Plus, it adds positional encoding, right? So the AI knows the exact timestamp of every single acoustic event.
Spot on.
But then, I was reading this part, and the paper notes that the AME is bidirectional.
Yeah, this is key.
It scans the audio sequence forward, and then it literally flips the time axis and scans it backward. Why in the world does an AI need to listen to audio in reverse? Because sound doesn't travel backward in the physical world.
No, it doesn't. But what's fascinating here is it comes down to the physics of sound localization in complex indoor environments.
Right.
When you or I try to locate a ringing phone, we rely really heavily on interaural time differences and interaural level differences.
Meaning the microscopic delay, like literally microseconds, between a sound wave hitting your left ear versus your right ear.
Exactly.
And also the slight drop in volume between the two sides.
Right. And in a multi-story house, that sound isn't just traveling to you in a straight, clean line. It is diffracting around corners, it's bouncing off hardwood floors, it's getting absorbed by carpets.
It's messy.
Very messy. So by scanning that token sequence bidirectionally, the model captures both the causal and the anti-causal correlations of those audio signals.
Causal being like the original sound wave itself.
Right, and anti-causal being all the reflections and the echoes. By analyzing the signal in both directions, the AME extracts this super high-fidelity representation of the entire sound field.
Unbelievable.
It parses all those microscopic interaural differences without fragmenting the timeline at all, which allows the agent to definitively separate the true source direction from all that reverberant noise.
So the Audio Mamba encoder basically completely solves the perception bottleneck. It takes in the whole soundscape forward and backward without losing the timeline.
Yes.
But, I mean, if the hearing is fixed, we still have to fix the memory problem, right?
Right. The junk data problem.
Because if the robot still has that outdated GRU brain, it's just going to dilute this pristine new audio data with the visual boredom of walking down a long hallway.
Exactly. So we have to leave the perceptual layer and move over to the memory layer. And this is where we get the Mamba State Encoder, or the MSE.
The MSE.
Yeah. This module completely replaces the old GRUs by shifting from fixed parameters to dynamic ones.
Okay, so with the old GRUs, the parameters deciding what to remember were just static weights.
Yes, static.
I'm sort of imagining a camera with a broken fixed focus lens, Like whether you're looking at a blank wall 3 inches away or a fast-moving bird way off in the distance, the lens just can't adjust.
It's a great way to picture it.
So the MSE feels more like a highly advanced predictive autofocus.
Exactly, and that autofocus mechanism is driven by the dynamic generation of parameters based on the current input.
Meaning it adapts on the fly.
Yes. Now, the math underpinning this, I know it sounds like jargon, but it relies on the discretization of continuous state space equations.
Discretization, meaning taking a continuous flow of real-world time and chopping it up into discrete, measurable steps so the computer can actually process it.
Precisely.
So how does the Mamba state encoder actually manipulate that?
Well, it applies something called the zero-order hold rule. And what this mathematical rule allows the AI to do is dynamically control the decay rate of its historical memory.
By adjusting a step-size variable, right?
Right. When the robot is receiving uninformative data like staring at that blank hallway wall you mentioned earlier, it calculates a much larger step size.
So it increases the decay rate of the current input, essentially telling the memory center, hey, ignore this, fast forward, nothing to see here.
Exactly. It just glosses over it. But the moment it detects a sharp, critical acoustic landmark, it shrinks that step size way down.
The decay rate drops.
Yes, and the agent focuses intently, heavily, incorporating that specific data point into its ongoing state representation.
So that snaps into this high-resolution, slow-motion capture the exact millisecond it hears something important.
That's exactly what's happening.
It's actively managing its own attention span, which completely eliminates that representation dilution we talked about.
It really does.
And this MSE architecture, it has dual-mode flexibility too, doesn't it?
Yeah, this is a huge advantage. During the training phase, the system uses a parallel scan algorithm. Because it doesn't rely on the rigid step-by-step bottlenecks of those old recurrent networks, it can actually process massive sequences of training data simultaneously.
Which makes it incredibly fast and efficient to train.
Incredibly efficient.
But then, when you actually deploy the robot-like, when it's out in the wild, trying to find a ringing phone in real time, it seamlessly switches to a single-step recurrent mode.
Right, because you need that. This guarantees low latency, real-time responses so the robot isn't, freezing up while trying to calculate its next physical move.
If we connect this to the bigger picture, it achieves a stronger perceptual modeling capability just from its mathematical essence. The robot can selectively forget the hallway, but perfectly recall the directional cue of that faint ringing.
Exactly.
So the math is elegant, the theory is totally sound. But what happens when you actually drop Samba into the arena?
Well, that's where things get really fun.
Because the researchers tested this on the SoundSpace's acoustic simulation platform, right? Which is built on the Habitat simulator. And they ran it through two massive public data sets, Replica and Matterport 3D.
Right, and those data sets provide a really crucial contrast. Matterport 3D consists of 85 real-world indoor environments, so it introduces a lot of natural chaos and messiness.
Right.
Replica, on the other hand, contains only 18 synthetic indoor scenes, but the precision of the geometric details, the lighting, and especially the acoustic material properties are vastly superior.
Way more precise. And they threw 102 distinct natural sounds at this AI. They tested it on heard sounds audio it had practiced with during training, but more importantly, unheard sounds, placing completely unseen scenes.
The ultimate blindfold test.
Exactly. So how do they measure success?
The evaluation relies on three specific metrics. The first one is straightforward. Success rate, or SR. Basically, did the agent successfully start at the target sound source?
Okay, did it find the phone? The second one is SPL. Success weighted by path length, which makes sense because finding the phone is great, but did the agent take the shortest, most mathematically efficient path to get there, or did it wander through 3 different bedrooms first?
Right, you want it to be efficient. And the final metric is SNA, Success Navigation Accuracy. This evaluates the strategic precision of the movement itself.
So it penalizes the agent for spinning in circles, bumping into corners, or taking redundant exploratory actions.
Exactly, and the results on these metrics are just staggering. On the Matterport 3D dataset, compared to the previous state-of-the-art model, which was called AV1, the Samba framework showed an 11.3% bump in overall success rate.
Which is great. But on the replica dataset, the one with the hyper-precise geometry and acoustics, Samba absolutely crushed the old paradigm.
Oh, it wasn't even close. For completely unseen scenes and unheard sounds on the replica dataset, the success rate jumped from 52.8% with the old model to an astonishing 72.8% with Samba.
Wow. A 20 percentage point absolute improvement in deep learning is massive.
It's practically unheard of for a single architecture change.
And the trajectory metrics prove it wasn't just getting lucky, right?
Right.
The SPL, that path length efficiency we mentioned, it climbed from 34.7% to 42.4%.
Yep.
And the SNA surged as well. This paints a picture of an agent that isn't just wandering aimlessly anymore. It is moving with absolute strategic purpose, tracking its state robustly, and just heading straight for the source.
And, usually when you see a 20 percentage point jump in performance, the standard assumption in deep learning is that the developers just threw millions of new parameters at the problem.
Oh, for sure. Just brute force it.
Right. You assume they scaled up the model size, making it computationally heavy and really expensive to run.
But the wild twist here is that Samba actually got smaller.
Much smaller.
It is leaner and doing significantly more with less. Let's look at that parameter drop.
The drop is substantial. The Audio Mamba encoder, so that's the module replacing the CNNs, it went from 0.7 million parameters in the old baseline down to just 0.4 million. That is a 43% reduction in size for the perceptual layer alone.
And the state encoder, the memory module replacing the GRUs, that dropped from 3.9 million parameters down to 2.7 million. It's a much lighter model overall.
It really is. And the researchers actually conducted a rigorous ablation study to isolate exactly why this lightweight model outperforms the heavyweights.
An ablation study, meaning they systematically stripped out the new components to measure the degradation in performance.
Exactly. They wanted to prove what was carrying the weight. And when they removed the Audio Mamba encoder, forcing the system back to using CNNs for hearing, the success rate for unheard sounds on the replica dataset plummeted.
It dropped from that 72.8% all the way back down to 59.0%.
Right. The perception completely collapses without that bidirectional global scanning.
Right.
Furthermore, when they removed the Mamba state encoder, so forcing it back to static memory updates with the old GRUs, the performance dropped to 71.0%.
Because the agent begins to suffer from that representation dilution again.
Exactly. It starts losing track of the goal amidst all the environmental noise.
So what does this all mean? The core takeaway from synthesizing this ablation data is pretty profound. The secret to pushing AI forward isn't just, brute forcing the problem with more compute or blindly scaling up parameters.
Not at all.
Better architecture fundamentally beats raw size.
It really does. Replacing rigid convolutions and static memory gates with selective state spaces, it just unlocks superior embodied representation capabilities.
Just smarter.
Exactly.
Yeah.
That compact selective scanning mechanism captures global acoustic features far more effectively than just stacking massive, inefficient networks on top of each other.
Which is exactly the breakthrough required for the real world, right?
Yeah.
So if you are ever going to put these AI brains into physical robots like search and rescue drones or home assistance robots, they need to be lightweight enough to run on low-power edge hardware.
Absolutely.
But they also have to be robust enough to parse the sheer chaos of a real physical environment.
They do, and Samba finally bridges that gap.
So, to recap the journey we've been on today for you, the AI navigation industry has essentially been stuck in a 5-year rut.
A deep one.
Right. The reliance on CNNs meant the AI was chopping up the timeline of sound, scrambling those causal echoes and frequencies.
Yeah.
And the reliance on GRUs meant the AI was constantly diluting its own memory, prioritizing boring empty hallways just as much as critical acoustic cues.
It was a flawed foundation.
But the Samba framework changes the math entirely. The Audio Mamba encoder allows the AI to scan a soundscape forward and backward, perfectly parsing those interval time differences without fragmenting the audio timeline.
Right.
And simultaneously, the Mamba state encoder introduces dynamic parameters, applying that zero-order hold rule we talked about to let the AI actively manage its own attention span.
Fast-forwarding through the junk.
Exactly. It fast-forwards through the uninformative visual noise and snaps into high resolution the moment it hears the target. The result is a lighter, faster, more computationally efficient agent that navigates complex, unseen 3D spaces with an unprecedented 72.8% accuracy.
This actually raises an important question, though. It forces us to look beyond just robotics and consider how we process our own environments.
Oh, interesting.
Because we are looking at a state-of-the-art leap in intelligence that was achieved not by teaching a machine to process and remember absolutely everything, but by giving it the mathematical framework to selectively forget.
Wow. Yeah, because the old models failed because they couldn't separate the signal from the static.
Exactly. They were paralyzed by representation dilution. They were completely overwhelmed by redundant environmental noise. By empowering the AI to dynamically control its attention, to literally actively ignore the irrelevant data, it achieved mastery over its
I
surroundings.
love that.
And, we live in an era of unprecedented human information overload. We are constantly bombarded with data, feeds, notifications, and we're attempting to retain every piece of input as if it holds equal weight.
We really are.
So, if we are now successfully training embodied AI to achieve peak performance purely by teaching it how to dynamically filter its memory and discard the noise, what does that reveal about our own cognitive bottlenecks?
That's a great point.
Perhaps the ultimate breakthrough for us isn't learning how to consume and process more information, but mastering our own art of selective attention.
That is brilliant. Because the next time you find yourself metaphorically blindfolded in a strange environment, just totally overwhelmed by the sheer volume of data, you should remember the architecture of Samba. The secret isn't obsessively feeling every single wall, it's knowing exactly which walls to ignore so you can finally hear the ringing phone. Until next time, keep diving deep.